Alright, ladies, I'm going to talk to you about measurements and error analysis in science. Obviously, when we do physics labs, you've already done several where we have done a lot of measuring. And so you could either measure really well or you could be kind of sloppy in your measurement. And the topic of today's video is about accuracy and precision. How do we describe that? How do we analyze it when we do a lab experiment? So let's get started. So first of all, let's talk about scientific measurements. Whenever we measure something, there are inevitable sources of error, and a couple of those have to do with instruments. For instance, our balance over here, and I'm going to go grab a pen. So if I grab a pen and we look at our balance over here, remember anytime you turn the balance on to start with, usually the first number that comes up is not 0. And so what you typically have to do is hit the tare, T-A-R-E, or the 0 button in order to get the balance to register 0 before you start putting a mass on there. So if you had forgotten to do that, that would be instrument error. You would not get the right reading for mass if you, for instance, piled something up on the pan of the balance. So we put a bunch of rocks or something here that we wanted to figure out the mass of. We put this on the balance and we got our value. It's not going to read the right thing if we forgot to zero the balance. Another thing that might cause us error if that's based on our instrument itself is instrument limitations. If we look at the digits displayed on this digital display, I believe this balance is displaying 2 digits past the decimal point. So if we needed a measurement that was accurate out to a 3rd digit past the decimal point, this would not be a good instrument to get that with, because it's limited to only those 2 digits. And so that would fit in this category right here of instrument limitations. A third type of error is measurement error. Notice that this nurse is apparently trying to measure the height of this student, and there's some kind of measuring tape up on the wall here. Well, notice she's sighting up along her arm and trying to read off a mark off here as to how tall that student is. Well, she's not going to get a very accurate reading if she does not get her eyes to where they're level with the measuring tape. So that would be an example of, the technical term for it is parallax error in that particular case, but measurement error, because you're not reading an instrument right on. Okay, so how do we describe accuracy and precision? The words sound very similar, but they aren't exactly the same. So let's talk about the difference between them. Accuracy is how close a measurement is to the accepted value. And the examples I chose in here were 9.8 meters per second squared. That's the value for the acceleration due to gravity on Earth. And if you had done a physics experiment, which you will in a couple of weeks, to measure that value, and you came up with this number, 9.79 meters per second squared, well, that is definitely close. And so that would certainly fit the bill to be reasonable to call it an accurate measurement. So we would say that those two measurements are, or your measurement of 9.79 meters per second squared would be accurate. Precision, on the other hand, refers to how small a difference a measurement shows when you compare it to a set of similar measurements. So here is what my example that I have written down here means. Let's say you were measuring the length of a line, for instance, and you set your ruler down against it, and you looked on your ruler, and you read off the tick marks, and the first time you read it, you got 0.813 centimeters, inches, whatever it might happen to be. So you wanted to double check your measurements, and you did it again, and you got 0.814. And you're like, well, they're pretty close. Let's try it one more time. And this time, for whatever reason, you got 0.879. Well, those 3 measurements are really not that close to each other. And so we would say this was not a precise set of measurements, because they aren't really close to each other. So precision has to do with how close the measurements are to each other. Accuracy has to do with how close they come to an accepted value. Now, if we look at an analogy that might help just give us a better feel for that, the dartboard analogy kind of helps us zero in a little better on accuracy and precision. So in darts, of course, the objective of the game is to throw these pointed objects at the bullseye. And the bullseye is this red circle right in the middle. So in the first example, there's 3 sets of darts that were thrown. They didn't hit close to each other, and they also did not hit in the bullseye. So they have low accuracy because they didn't make the accepted value, and they have low precision because they aren't close to each other. In the second example, here they did land close to each other. So we would call that high precision, but because they didn't land in the bullseye, they have low accuracy. In the third example, now the darts have landed pretty close to the bullseye, so that counts as high in terms of accuracy because they're trying to hit the standard mark, but they aren't close to each other. So that's low precision. And the last scenario has all 3 darts in the bullseye, so high accuracy, and then they're also close to each other. So that would qualify as high precision also. Now when we're specifying errors that we get in our labs, and I'll always ask you to do this, we'll have 2 kinds of errors that you might have to come up with a numerical value for. One is percent error. And we use percent error when we are comparing a value we measure to the actual value. So for instance, for the acceleration due to gravity, we know that actual value is 9.8 meters per second squared. If we had done a measurement and we measured a value of 9.7 meters per second squared, and we wanted to find the percent error between those 2 numbers, all you do is take the difference between the actual and the measured value, which is what I've done here, and then you divide that by the actual value. So my actual value is 9.8 meters per second squared. I take the difference between that and what I measured, divide by the actual value, multiply by 100%, and that gives me percent error of 1%, which is really good. If you normally get percent error between 1 and 5% or so, I'd say you were successful at doing that measurement. Now don't get hung up on the fact that I said measured minus actual in my equation, but did you catch that when I substituted them into the actual calculation here, I put actual first and measured second? That's okay. You're really only concerned about the absolute value of the difference between the 2 numbers. One other way that you might express error is in percent difference between 2 values. This would be if you wanted to compare how close 2 measurements are to each other rather than to a standard value. So just each other is all you're caring about. So now you look at percent difference. And for this, the equation looks kind of complicated, but it's really not as complicated as it might look. I'll tell you what, I'm going to erase that line there. Kind of messy. Let's get rid of that. Okay, back to the pen. Alright, so what we do is take the difference between the measurement number 1 and measurement number 2, and then we divide it by the average. And since we've only got 2 values, it would be add the 2 measurements together, divide by 2, so that you take the difference divided by the average times 100%. And so if I were comparing 2 values that I got, 8.6 meters and 8.3 meters, here in the numerator I've got the difference between them, and then I divide in the denominator by the average. 8.6 plus 8.3 divided by 2 times 100%, and when I perform that computation I get 3.6% for my percent difference. And again, that's not too bad. If I get a percent difference like that, I'm feeling pretty good. If I got a percent difference of say 50%, I'd say, you know, I probably ought to go back and restart that experiment. So the important thing to take away is what's the difference between precision versus accuracy. So you want to know that. And we'll try and get it written here. Precision versus accuracy. And then you also will be calculating, well, we'll go back and fill this in a little bit. You'll also be calculating percent difference and percent error. Percent difference you use to compare two measurements to each other, and percent error to compare your measurement to a standard value. Thanks for listening.